So the first exercise, what we're going to do in it is it's just going to build a really simple state and transition simulation model, just get you used to the software. You're going to go through the steps more or less that I did in the dice example, the game board example. But the model we're going to use here is a very simple model. It's the one that's I showed in the earlier slides where I had three possible states. It's a forested system where I have conifer, deciduous, and mixed. So this is the figure from that I showed earlier. It's actually from that foundational paper. So you're going to be implementing a version of this. So that's going to be your landscape with three possible states. This is the diagram that corresponds to the probabilities we're going to have you put in for here. So I'll let you look at the exercise, but essentially we're going to have a mixed state which starts at age 10, conifer state that starts at age 20. We have a succession transition that has a probability of 10% per year once your age gets to a certain level. And fire with different probabilities depending on what your state is. And those are all done with probabilities. We're also going to throw in one transition that's going to be target based. So that's what you're going to work on. The model is going to be aspatial in this exercise. So we'll show you how to create one of these models to run aspatially. I don't think I have anything else to add. The rest is sort of in the exercise. I'm going to do it right like this. It's going to be a lot easier. This is just some of the terminology that's used by SynchroSim. So I'm just going to glance at it. You have it in your slides. You can look back at it as sort of a glossary. But the idea is that we have this concept of a library, and it's a container. It's a .sim file when you start, but if you'll see as the exercise progresses, there's usually a couple folders that go with it that carry around basically your spatial data to go along with it. But the SIM file is actually a database. It's a SQLite database, and it's designed to store all your inputs and outputs and keep track of the relationships between them. So you'll see that build. But that's what we call that a library. And then within each library, you can have one or more what we call projects. And actually in this version of the course, projects are kind of an advanced feature. We don't use them very often, so it's hidden from you. You always see this sort of node called definitions. You could actually create multiple of these projects. Each one is like a separate library within a library. So it's like you usually have one project per landscape. We tend to have one landscape per library, so we don't use this definition or this project feature much anymore. You will need to understand it if you get to the end of the course and you start working with the command line version of SynchroSim, because it kind of requires you to understand this. And then within each project, so we have one of them in all the examples here, you can have one or more of these scenarios. And a scenario is just a collection of model inputs. And after you finish a run, it's also the collection of your outputs that go with it. So the outputs that are paired with your inputs. And these are all SynchroSim concepts. They apply to any model you run in SynchroSim. Then a couple other things within a scenario, or actually within a project as well, you can have these things called data feeds, or actually let's start with data sheets. Data sheets is just our term for a table of data, whether it be an input or an output. And then we have this thing called data feeds, and the distinction is subtle, but sometimes you have several data sheets combined into a single data feed. It's pretty rare. Usually it's one to one. But if I just look at, let's just look at what we just went through in the course here. So we're on exercise 1. By the way, if you go into these folders, this is a kind of an unusual example. There's always a library, which is the solution to the exercise. Let's go to exercise 3. This is more typical, where you have the file you're meant to start with. It's the version .sim file with no suffix. There's one called start that if you mess up your exercise 3 as you're going, you can always get back. It's kind of a copy of the, you'll see it's the same file to start. And then we put one in there that's the solution. That's kind of the pattern. In this first exercise, you started with a blank slate, so there was no start or sim file. And these are the folders that go with them. So you can see the solution file has an input and an output folder, and these will contain spatial files when we sort of get into that later. So if I'm in, what was I looking at again? Exercise 1, I was just picking this, I was opening the solution file. So I was just showing you what a data sheet and a data feed are. So you go in here and most of the time, in fact, if you click on this data sources tab, you can see a list of all the data feeds that are part of a scenario in the StSim package. So one of the, so this is one, you got transition targets. It's a table of data. If you went back over here, initial conditions, non-spatial that you filled in, this is actually one data sheet consisting of one data feed consisting of 2 data sheets. This is one of the sheets, and this is actually another table in the database actually underneath that's got a single record in it, but it's so there's actually 2 data sheets here. So that's just part of the concepts. Let me go back to my thing. And then libraries, projects, and scenarios can all have data feeds associated with them, or settings or inputs. You really haven't looked, you've looked a bit at that, but if you go in here and you right click and you go properties, you're going to see all the inputs associated with that project. Actually, if you go in the library and you do the same thing, you get a list of the library settings. And if you go in a scenario and click properties, you get a list of the settings for the scenario. Most of the time, you're not changing settings at the library level, only at the project level and the scenario level, which is what you experienced in this exercise. Now, the project level inputs, those are what we call sort of definitions. That's why we labeled it like this. And they are the kind of currency that you use across scenarios. So they're often simply labels, labels of your state classes, labels of your transitions, labeling for your terminology, labels for your strata. So they're things that you got to set once so that your scenarios, when you compare them, they're all talking the same language. So that's the purpose of these. Most of your inputs, those you found in this exercise, get set at the level of the scenario. So any questions kind of about the basic syntax? I don't think there's anything else. Yeah. Well, the last thing is just with results and scenarios. So if we look in here at the exercise you just did, you can see that you eventually created 3 scenarios here, all with different settings. I don't know if you noticed this, but if I created and if I took one of these and went copy and paste, this is a scenario. It only has inputs in it. I can tell it only has inputs. It doesn't have this little green arrow beside it to tell me I ran it successfully. And so these are all scenarios that have been run. I can tell that by that icon. But after you run a scenario, if you open this up, there's a list of results. So this is actually a child scenario of the parent that has the actual output from that run that you did at that particular date and time. And in fact, if I went and opened this scenario, and let's just run it for, to do it quickly, for one Monte Carlo, and I ran it again, it's done very quickly. That's a new run of that scenario. I've changed the inputs. It keeps a chronology of all your runs in here. And in fact, what it does as well is it does a snapshot of your inputs. So the one you guys ran earlier, I ran it with 100 Monte Carlos. The one I just ran 30 seconds ago, it's stamped down that I ran it with 1. So there's a full record kept in the library, all your inputs and outputs, et cetera, et cetera. So that's one point I just wanted to make. Let's just look at some of the things you set in here. So you kind of got the idea that we had to list our strata, you set up your terminology. One thing to point out is that, you know, when we're talking conceptually about state and transition models, we're always talking about a state class. And that's what these are. These are your 3 state classes. These are really the things you're modeling, but you notice that you had sort of 2 dimensions in which you could label these state classes. You could give them a tag, which actually over in the terminology was the label X and the label Y. So these things could each have, you know, 2 labels to every box, so that when you're sort of looking at them in the pathway diagram, you get them sort of labeled in 2 dimensions. But those are just labels. There's not anything special about them. It's just a convention we've decided to allow you to label state classes by 2 dimensions. And that was sort of the purpose of defining the state classes in this 2-step process. What else did I want to point out? The transition pathways in this model. You guys had a fairly simple model, right? Just with these 3 state classes. And I think the exercise showed you that, you know, you can double click on a box and see the pathways leaving that state class, but you can see all your pathways together, yeah, on one screen, right? And typically this is where we work. We rarely work with models of any complexity off of that diagram anymore. But one thing you probably noticed when you're setting the age is that actually it's only these 4 fields that are the required fields for a transition pathway. You have to say whether it's coming from, where it's going to, what the transition is, and the probability. And putting an age limit on some of these transitions was an optional field, but if you right-click anywhere in the grid, you get a list of a whole long a slew of different optional features. And this is a feature you'll see again throughout SynchroSim, is that required fields come up by default. You know, for example, if I go on transition targets, there's only a type, harvest, and a target. But if I right click here, I could specify targets by time step. I could specify them to vary by strata. I could specify them to be sampled from distributions, et cetera, et cetera. So you'll find as you go along that there's a lot of complexity that's hidden from you when you first open it up, but by right-clicking, you can see the full breadth of options that are available for most inputs. And I'll just point out a few. We don't go into it in the course, but you can go to our online help, and it describes these in more detail. I'll show you that in a minute. But we can limit transitions to only occur when a cell is in a certain age range. We can also tell it to only occur when there's been a certain time since another transition has occurred. And that's a little bit more complicated. We won't get into that, but basically you can make them contingent on the time since any transition. That's a fairly advanced feature. You can also tell it what to do to the age and what to do to the time since transition after the transition occurred. So by default, when you have a transition in this model, it's when you go to the new state class, if you looked over here, when there was a fire transition from conifer over to deciduous, by default, it reset the age to the starting age of the destination class. But you can do a bunch of other complex things where you can tell it to shift the age by a certain amount, or to reset it, or to maintain its age after transition, and so on and so forth. So we don't go into that because you can spend a lot of time in here, but just to show you the richness that is available there in defining these pathways. That's a little FYI. There is, I think we refer to it at the very end of the course, but there is StSim.net. There is a website for StSim. It's a little primitive at the moment. The one thing that it's useful for is This is the documentation for StSim. If you go into this properties link and you look in here, all the scenario properties, and I go to the pathway probabilistic transitions, and here's a list of all those optional fields. So how the age shift, how the age reset, how all those things I just showed you work. The details, a lot of them are in here. Now this thing is a little out of date. We're planning on working on it in the next couple of months to bring it up to date. But a lot of the basic inputs you can find descriptions of them on this documentation site. Another thing I just wanted to point out is when we were looking at these transition pathways, you probably noticed, I think the exercise took you through it, that not all of them have probabilities, right? We decided to set harvest with using transition targets. So what we did is we just set the probability to 1, and then we overrode that probability by using a target. So we could actually have set it, in this case, to just about anything we like. But we have a convention of generally setting transition pathways to 1 for those that we're not using a probability for. And you'll see a little later why we choose 1 when we get into some of the other exercises. But just to point out again that the probability can be overridden by other fields in different circumstances, and you saw that in this exercise with the target. Last thing I just wanted to go over is the charting again. So you were led through creating a chart, but I just want to describe that in a little bit more detail. And all of this is, our way to try and convey to you the basic features of SynchroSim quickly. I mean, it's not the focus of this course at all. So you'll see that the exercises really don't focus on the mechanics of using SynchroSim and setting this stuff up. But you'll see here, as you saw, you can create a new chart. When you start with a chart, here's the basics, how a basic chart works. You can choose between a line and a column chart. I don't know that we do any column charts in this course, but well, maybe I can show you one in a sec. You can set the time range, but the most important thing is you have to pick the variable you want to look at. Now, the basic output of any state and transition simulation model is the state of every cell, the age of every cell, the time since transition of every cell. So basically the state and the counters for every cell, and also whether or not a transition occurred on every cell. That's basically it. You can look at the states, you can look at their counters, and you can look at the transitions. So you have to pick from one of those when we're doing this aggregated non-spatial output. We have to pick which of those 3 we want to look at. And so typically we're looking at, say, the states, and you can pick your area. And then what you can do next on all the charts, and you'll see that more things get added in the later exercises, you basically can say, what do I want to split that area out by? That's what this disaggregate is by. So in this exercise, we said we want to see the area disaggregated by state class. And then we can also choose which things to include in our sum of the area. It's a filter, really. And so we could, for example, look at, let's just say, only conifer and not deciduous. Or maybe we want to look at whatever. So we could do a filter like that, and we could hit apply. And this is now showing me the total conifer area over time. And we could, if we had age in there, we could also tell it, for example, to only look at conifer older than age, say, 40. So we could do that. And there we've got a graph of the conifer over age 40, which, as you probably learned in the exercise, we run out of older conifer when we start harvesting. In fact, if I take this with no timber harvest, let's just add that to the results. So that's another thing you can do, is you can take old previously run scenarios, you can right click on them and remove them from the results and add them to the results set. And so now I've got the no timber harvest overlaid on the harvesting scenario, and I can see the difference in my age 40-year-old and greater conifer. And so the transitions and all the others work the same way. You basically pick a variable and you can disaggregate, and then you can filter and create these charts. And you can create as many of these charts as you want. You can save these and give them a name, conifer, old conifer. Right, you got the idea, and you've got another chart that you can save in your library. Another thing I was just going to show you is, I think when you did your runs, we never dealt with age, but if you look over here, you can set up your ages. Was the original exercise, did it have age set up in it? I can't remember then. But I don't believe it had groups, but you can pick over here. If you notice, when I was looking at this conifer, it was grouping my ages into categories, and these are configurable as a definition. You can set your breakpoints over here. I could change them, actually. I could go, 20, 30, let's just do that even. And I could regenerate this, and it should regenerate the chart. Oh, it's taking a while. And you can see it's changed the breakpoints, and now the old breakpoints don't quite work. So here's the amount of area, 30 and older. I have to go change my title on the old conifer, but you get the idea. The last thing I just wanted to show you is how to multiprocess. So when you were running these simulations, you were, like most software out of the box, it's only using one of your processors on your computer. And even the most basic laptops now have at least 4 processors. Most of them have 8 now. You can look at and see how many processors your computer has, actually. I think where we can see it in the task manager, right? That's where we go. Go to the task manager in Windows, and you go over here. You can see, where do I see it? Processes. Now, where is it now?
I think you have to go to the resource monitor at the bottom, yeah.
Resource monitor. And where do I, oh, here.
On the right, yeah.
On the right here, it's showing you, in my computer, this is a 4-core machine. Most Windows computers have 2 processors per core. So I can see here there's one, if you look down here, there's actually 8 charts. There's CPU 0 through 7. So there's actually 8 processors available for me to process on this computer. And if you were to run Excel or to run any Word or whatever, they launch on one processor, and 7 of your processors generally aren't being used. They're used by your operating system and so on. And so there's a huge advantage to be had by taking advantage of all the processors available, even on a laptop. And so this is one of the features in SynchroSim. It has this built-in multiprocessing. And so in this first exercise, the runs were so short and simple, we didn't bother. But you'll see, I would tell you, actually, when you start the next exercise, to turn on multiprocessing for the rest of the course. And so we just do that by turning this on. And there's a drop down here to say how many cores you want to, or processes or jobs you want to make use of. And I believe it defaults to 1. It figures out on your laptop how many there are, and it does 1 minus that to leave you 1 for doing stuff while your runs are happening. And so here we would set it to 7. The exercises we've done in this course are really designed to run on 6 cores, so I usually set it to 6 when I start. But that means that when I run this simulation, this is the one with only 1 iteration, but if I had ran it with 6 iterations and I run it, you'll see later in the exercises that it will automatically put each of the Monte Carlo realizations on a different core and take full advantage of all the processors on your computer. When we step up and do larger landscapes, we do a lot of our work now using cloud computing. We use Amazon in our case, AWS. And so we do that because we can spin up a machine that looks and feels just like this on Amazon. But we can dial it up to have 50 or 100 cores and run one of our larger simulations over a larger landscape very quickly, even though it's a huge landscape. And then we can turn the virtual cloud computer off. And so we can do huge runs very quickly for just a few dollars a run. So that's a big part of how we do our workflow. I mean, every government agency is a little different in their ability to access that kind of computing power. I don't know what it is for you and the folks here. Some people have high performance computing. You know, our software runs on Linux to support that as well. But just to let you know that there's sort of this whole, a lot of work been put into being able to run large landscapes efficiently using multiprocessing. Anything you want to add, Leonardo or Louis? So what was the effect of the composition of the landscape on the composition of adding timber harvest? So what you should have seen in this model, right, if we go over here, let's take off the bonus one here for now. So we'll just add these two and we look at the states and transitions diagram. So you should have seen something like this. So the blue is no harvest and the red is 20 hectares a year. What you'll notice is that the harvest is targeted at 20 hectares a year, but in year 6, it basically runs out of available, it needs conifer greater than age 30 to harvest. If it can't find it, it won't do it. So the harvest basically drops down to 0, and you'll see the conifer here gets very low. And actually, if you look probably at my conifer, my old conifer, right, that I just did here, it should actually show, there it is, the old conifer, which I did up earlier, right, it shows exactly what I thought, that in the harvest scenario, it drops to 0, even though there's a bit of younger conifer left. There's no old conifer left. And every stick of old conifer that comes online later in the model simulations gets harvested right away. So there's this low sort of 2 hectare a year harvest that occurs later in the simulation, right? And so the result of that is, we see the shift of less conifer on the landscape in response to our harvest, which is what we would expect.
Also, Colin, the conifer that does survive any harvest gets burned half of the time or something like that. So the poor guys have no chance.
Right. We have a very high fire level on this. What was it again? I don't know. Actually, we can tell. If you wanted to see the proportion of harvest of fire that's occurring, we could just do a chart. And this is one of the huge strengths of, I would argue, of StSim, is it's running in the SynchroSim environment that has this, like we find as modelers, really hugely valuable ability to drill down into your model output interactively. This is not just for novice users or for, sort of public engagement. This is using this charting is a feature that we use every day in very sophisticated modeling to figure out what's going on in our model and to see if we agree with the behavior that we're seeing. So this is an example. So if I wanted to see how much fire there was, I could go down here and say, look at area, and I could see, I don't need to disaggregate, but let's just include only fire. And let's do it as a proportion of the landscape. And what did I do wrong here?
Select proportion under transit.
I want the area. I want the.
Unclick that one.
And so we're burning about 6% of our landscape per year in the simulation. That's the average. And that's the average, if you look back at your diagram again, pathway diagram, we can't actually know what that is until we do the simulation. because we have differential. If we look at the fire, here the fire, we have 5% of the deciduous, 8% per year of the mixed, and 15% per year of the conifer. So the overall fire return interval, or 1 over that, which is the fire probability, is the combination of all these and is driven in part by the composition of the landscape. So it can be different on different simulations, but here we find it kind of equilibrates at 6%. Just to go through this is the bonus question. So what we did in all that was asked of you in the bonus question was to model fire suppression by basically doubling your return interval, which meant halving your fire probabilities. That was what my intent of it was. And so if we look at the original scenario here, and we look over at your original, probabilities, we had for fire, we had 15, 8, and 5%. I just created a copy of that scenario, and I went over here and I have them so to be 7.5, 4, and 2.5. They're reversed in order here. But I put that in and reran the model with the fire cut in half, essentially cut in half from a probability perspective, not necessarily from a total area perspective. And we would have got these kind of results. Let me take off the no harvest and add the results with that fire suppression. So we would have got something like this. This is without the error bars on it, but you can see with the fire suppression, we get roughly half the fire that we did, and we have a corresponding change where we see more conifer, less deciduous. Basically, the landscape's being allowed to succeed further into the mixed and conifer classes rather than all being stuck in the deciduous and then getting burned quickly. Any other questions or comments? So this is a spatially reference. No, well, it's not even reference. This is a non-spatial model, right? Even though we ran it with actual cells under the hood, we parameterized it, not being specific about where the cells, how they were initialized. We only initialized them non-spatially. And so it only makes sense to look at the results in the cumulative across the entire landscape. And we don't run models that often this way. In fact, well, that's not true. We don't produce final products that end at this point very often anymore. But often you'll see that the models we develop, much like you're doing in the exercises in the course, we very, very often start our projects with non-spatial models, get the dynamics down just aspatially, and then add the spatial dynamics as a second phase. It's a really common way of building even very complex models. It really sort of allows you to manage the complexity in sort of a phased approach. So that's one thing we do, but there is the odd group that, there still can be a use for non-spatial, aspatial models in an applied sense. And so one of those examples is just a group that we've been working with for 20 or more, probably more than 20 years, probably longer than you, Louis, I think. And that's a group called the Landfire Program in the US. So this is a program that's set up to basically, in a nutshell, develop fire fuel layers for the entire US at 30-meter resolution to update them continuously. And there's a lot behind this program. There's one tiny piece of it, which is the vegetation piece, where as part of Landfire, they have generated a series of state and transition simulation models for every ecological system in the US. So they've gone across the US, they've created, they call them biophysical settings. I think they're a lot like your archetypes. They have about 600 of those, I think, in the current iteration. So they've gone across and they've, if we look, they've created, well, just before we do, and for each one of those biophysical settings, they've created a simple aspatial model that looks something like this, that has at most 5 states. And they use these models to make projections of what the reference conditions would have looked like in that ecological system or biophysical setting, they call them, pre-European settlement. And the purpose of that modeling is to kind of create a benchmark for the vegetation condition in each one across the entire US, that they can then say, how far departed are we today from where we were in reference? So they have work that they've done on measuring departure. Louis been very actively involved in this. And then they can use that to set targets and measure progress towards achieving goals of restoration, or often in terms of fire fuel reduction. So if we look, there's 500 of these map of these different systems. Again, they're a lot like your archetypes. One of them that we have a model for is called, just let me show it, I'll just give you one example that I pulled up this morning. So demonstration. This is one of those several hundred descriptions. They have documents like this online, but this is, one in the Western US, North Pacific, dry Douglas fir, forest and woodland. They have a description of it. They have estimates of the fire return intervals, pre-European settlement based on data sets. They have some other stuff in there. And then they divide it into classes, but ultimately they have created a set of these StSim models. So again, this morning I went to their website and I actually downloaded their models, and I can open up one of those right now just to show you if I can find it. Let me just see, I think it's probably in my recent libraries. Do you see reference condition there? Oops, I moved it. Okay, now I know where it is. So land fire BPS. So this is another library. I now have 2 libraries open, the original exercise 1 and the second one. So in this library, they have literally, 600 or 700 of these models. Each one is on a different strata, I believe. If you look in here, they've got them all here as different strata. But I this morning pulled one of them out. This is the one that I talked about, North Pacific. And I ran it. It runs very quickly. And I can look at the projections. Actually, I have to add it to the results. You can kind of, this is a run that they do. This is what they do with these models, is they run them for, actually they run them for 1,000 years, but they try and run them to equilibrium under these reference conditions. Actually, I should show you the model just so you get a sense of its complexity. So this is what these models look like. Actually, I have to find the right one here. No, I don't, if I open up the right scenario. Oh no, I left them all in there. That's what I did. So
yeah, it's 1035.0. It's written right there, 1035.0.
Right. So I got to find 1035.0 in here. There's system.
There it is.
There it is, 1035.0. So this is what one of their models looks like. So it's a 5-box model. They say they just move this particular biophysical setting through these 5 states. So you start in this young early state. and then through succession, you can end up in this middle-aged 20 to 59-year-old closed state, and then you can age further. And then if there's, let's just take a look, the kinds of transitions they have. If you're in this mid state, you can have surface fire, or you can have different fires occur with different probabilities. And, the replacement fire can set you back to early, whereas the surface fire doesn't change your class, and the mixed fire moves you from closed to open. So it opens the canopy, and so on and so forth. So, very simple models, not much more complicated than the model you just developed. And these are used, this program's been going for 20 years. So there is a place for simple aspatial models, particularly if you're trying to set up something like this, which is a national program, which is a very, and this is not it's to parameterize 600 or 700 of these. They do them through workshops and experts and stuff like that. It's been a big multi-year endeavor to get to the point they're at today.
Colin,
Yes.
and Anna, I was going to devote a few slides in the workshop in February, the conference, on the land fire project. To just summarize it in 10 minutes. We can't say a whole lot, unfortunately, but we show you a map of ecological departure and all that. I'm actually responsible for 120 of those models in the land fire project and the description. So.
But you can see, they have transitions that are, I'm looking across all their things, but they're a fairly basic set of transitions. They're just using probabilities. They're changing the way the age is reset, sometimes just a little different, and sometimes they're making them conditional on time since transition, which is similar to making them conditional on age. So not very much more complicated than the model you just developed.
Yeah, and they're strictly pre-settlement. There's no management. There's no invasives. There's no nothing in them.
Right. It's part of the reason they're able to make them simple. So any questions?